things I've just seen so many times that I don't really forget it anymore.
But that's why we did it the way we did it.
Like the plus
That's exactly why we did it this way.
I saw so many calculus videos where they say, "Oh, can't forget plus c."
Oh, you're talking about the notation?
Yeah, that and what is it? Rank plus nullity equals dimension. I actually wrote that out over and over.
Well, remember what Neumann said. You don't learn math, you just get used to it. I think there's a lot of truth to that. All right, so for this one, there weren't too many problems on it. I would only say there's 2 sticking points. And the first one was how to easily show that these 2 things are roots. I did this on purpose. I gave you the roots. Just in case you got stuck, you could continue on the problem, you have the roots. So how do you do that easily? And the second is to check that your diagonalization really works, because people were messed up with the order of their eigenvectors. If they weren't placed right, then it didn't seem to P inverse didn't seem to give you A, so it can drive you crazy. So I'm going to show you how to do that. The mechanics is not, this everybody seemed to get okay. You subtract lambda off the diagonals, and then you get the characteristic polynomial. And here's the easy part. How do you show lambda equals 1 as a root? Just plug it back in there. Put it in there and see what the number comes out to be. And how do you show lambda 2 as a root? Put it in there. So you don't have to factor or do synthetic division or go on your calculator and figure out a way to solve this. You can just plug those roots back in there and check that they work, and then you're done. So that's the easy way to get out of that issue. And it's quick. The second, finding the eigenvectors, that's the beast. But most people actually were able to get the eigenvectors. And so it's just, again, a copy and paste of the null space. You're really finding the null space of A minus lambda I. So it's a copy and paste of what we just did for null space. So you get those 2 vectors, and those are your 2 eigenvectors. Now here's the problem. If you go this direction, and you didn't place the order of your diagonal matrix correctly, then maybe the answer that you come out with is not exactly A. So you can start pulling your hair out saying, I don't know what I made a mistake on, it's not exactly A, I'm stressed out, I'm getting a Z right there. But what you could do is notice that all you really have to do is show that P inverse AP is a diagonal matrix. That's a way to get around worrying about the order of all your eigenvectors in the P. So no matter what order they are, they're still going to give you a diagonal matrix at the end. So it'll always work no matter what you placed your order as. And so I just went on a computer and I checked P inverse. You can do the inverse on your calculator. So save that on your calculator, punch it all in, and I turned out to get a diagonal matrix with the eigenvalues going down the diagonal. If that's what you get, a diagonal matrix with the eigenvalues going down the diagonal, you did it right. So 2 methods to cut down your time and aggravation on this problem. And this one, I went over this in class before, but this one, I didn't find an issue on the first part. That was not a problem right there, just plugging in that P of t. Where the trouble started was thinking of this as a linear transformation. And maybe I did the wrong thing. I showed you a way to do it quickly, and maybe that's not a good idea. So I'd probably advocate that you do these 2 separately, just to keep it all straight. So what you're doing is you're trying to show this fact and this fact together. So I'm just going to start with the first one. T of a mess is 2t minus 1 times the mess. That's a definition of what t does to a polynomial. So it doesn't matter if there's 2 polynomials inside there. You still do apply it the same way. Then, well, I can split that up into pieces by distributive law. And it just turns out that this person right here is Tp of t, and this one here is Tq of t. After I used distributive law. So it fell out. This one is also the same. T of the mess means take 2t minus 1 times the mess. Doesn't matter what's inside the argument. That's what you're supposed to do. You operate by doing that. Then C times this piece, well, I can rearrange them, right? I can turn these two around because multiplication is commutative. So those rotate around, and this turns out to be TP of t. So that one works too. I saw aha moment right there. This one, my feeling was it was more procedural. So my guess was that this one fell apart because it was exam 3, it was towards the end of the semester, and it just fell off of most people's plate. Does that sound right? I'm guessing, because I didn't get a chance to really ask you because I also got really busy at that time of the semester, but it looked like it when I saw people kind of freezing on that part. And they didn't freeze on finding a null space, and they didn't freeze on finding eigenvectors, which are, I think, much more complicated. The only answer I had is they just froze on this because they didn't get to it. All right, so how do you do this? You plug in the basis vectors. So the first basis vectors in P2 is E1. It's just 1. That's a polynomial, a constant polynomial. And you plug in 1 for the polynomial, and you get this. And notice I've expanded it out with all its coefficients. So the -1 goes here, the 2 goes here, the 0 goes here. How do I know that I have a t cubed term to deal with? Well, they told me. They said that the inputs are going to be in polynomials of degree 2, and the outputs are going to be polynomials of degree 3. So I'm looking at the output of my t. It's got to have at least a cube in it. So that's the second one. I just take E2. E2 is the polynomial with just t to the 1 power. Plug it in. I do the same thing I did before. If it looks like it's copied and pasted, it is. T3, E3, it's t squared. Plug it in there. I get that last vector. And then the matrix representation are t of E1, t of E2, and t of E3. Is easier than finding an eigenvector. So